Hello everyone. My name is Hiren Solanki, and welcome to this problem solving session of this course, Advanced Geomatics Engineering. This course is offered by Swayam NPTEL portal, and now in this third week, we are going to see about remote sensing data. So in the earlier 2 weeks, you have gone through the content like digital photogrammetry or photogrammetry related stuff where you how to take a photographs using stereoscope, two stereoscope images, how to find their elevations, how to find relief, parallax, and all those things we have learned. Now, from this week onwards, we will more go into remote sensing techniques, data sets, and its processing. So, in the first week, we will start with basic remote sensing, where I will introduce you about the how we can collect the remote sensing data through satellite, and then after we will go through some concepts related to remote sensing, and after that we will solve some numerical questions on that, and then after we will see some of the practical uh, parts like how to process those data using QGIS software. So let's get started. So basically, when we talk about remote sensing, so remote sensing is like getting an idea about some object without being in contact with that particular object. So let's say if we talk about our sense, then you can see like when we see someone through eyes. So our eyes are like best sensor. So we can visualize the different things that let's say if we are looking at some kind of leaf or let's say some flower. So we through our eyes we can say that whether that flower is fresh or not, or whether that leaf is like a green leaf or this like dried leaf. So that kind of things we can say. Now, when we talk about other like senses of us, let's say a nose. So without being in contact with food, also we can see like we can smell the food, and we can tell about like roughly like what kind of food it is. Apart from that, our hand or like when we do touch something, so in that case, what will happen? We have to touch the object. So that is not being considered as a remote sensing because we are going. So we are going in touching the particular object. That's why uh, we it is not considered as a remote sensing. The main idea behind the remote sensing it be without being in touch with the object or the phenomena. So when we talk about remote sensing, it is the art, science, and technology of obtaining reliable information about any object, let's say tree, buildings, or any kind of environment. Environment, it means like a water body or forest area and something like that. And then by collecting the data and recording the continuous data over the time, and then seeing what is happening, measuring and interpreting the imagery, and then digital representation of this energy patterns which we derive from those particular systems. So remote sensing instruments, it collects information about the object without being in contact with the object. So here you can see there are different platforms. Let's say one platform is let's say your aeroplane. So it can sense the trees which are there below it. Then after we have this satellites which are also away from the satellite, which is monitoring the entire Earth without being in contact with the physical contact with the objects or the features or phenomena. So basically, if we consider the remote sensing as a whole, so the as a system it looks like this when we have one energy source which is sun or any other thing. So if we are getting the energy from sun, then it is considered as a passive remote sensing. And if we have our own energy source, then it is known as a active remote sensing. After that, from sun energy will radiate, and that energy will go to the atmosphere. So from sun it will emit the energy, that energy will go through the atmosphere, and then it will go to the object such as buildings, roads, grass, water, forest. And then after interacting with the object, that energy will go back to the sensor, which will like go back to satellites. So when it will go to the satellite will record the energy which is being reflected from the ground object, and based on that we will say like how much energy we are getting back at the end. So that is a like that we are getting the information about the reflectance value of from the object. Now here when we talk about what kind of energy is being emitted from the sun, so when then the concept of electromagnetic spectrum will come into picture, and that we will learn in the in subsequent slides. Now once the energy will go back to the satellites, then after what will happen that it will transfer that particular information to ground antennas, and that ground antenna we collect those information, it will process it, and then we will make a application out of it. So when we talk about anti-system, so we have first one is the energy source, then the medium through which it is going, which is our atmosphere, then the interaction with the object at the ground level, then going back to the sensor, and then it will go to the set like some reception centers where it will receive and process the data, and then we will do the interpretation of the data, and then we'll make an application out of it. Once we made some applications, then we will measure whatever the data product which we have gathered from the remote sensing images. We will compare it with on ground things. Let's say we have captured the image about like a forest. So now we will go to the forest, and at some location we will do our validation that whatever the data which we got from the remote sensing, is it true or not. So it is possible that because of some like problem, let's say you have some atmospheric interruptions, you will not get the proper images, and because of that what will happen that the ground level information which you want, you will not get it. So this is the validation step which we will do at the end to validate our remote sensing product, which is known as a in situ measurement. So this we will do using the spectrophotometer, which will measure the radiance of the object which is be kept below. Now, when we talk about the platforms, we have various aerial platforms which can gather the remote sensing data without being in contact with the object. So the first thing, like kind of platform will be like ground-based platform where you have your drones, which are normal drones, then hyperspectral drones, then lidar sensors, which has been mounted on drones, and then some optical sensors. So these are all like ground-based measurements. Then we have airborne measurements where we use these aeroplanes, helicopters, and then fighter planes or some other which are at around 10, approximate 10 to 12 kilometer range. So that is known as airborne. So there also we can fit different kinds of sensor like lidar, SAR, hyperspectral. So that sensor we will attach along with the aeroplane or helicopter, and we will get the data about the land or the earth surfaces. And then if we go up in the sky afterward, then we have spaceborne sensors, which will be like satellites and the space shuttles. So which will give the idea about entire Earth, because other using ground-based and airborne, we cannot cover entire Earth very quickly. So for that, it's like we are using satellite constellations, which will give us the continuous data and the like overview of entire Earth as a whole, which will help us to understand the earth, how the earth is responding to the various phenomena which are happening, whether it's a climate change or something else. And then after once you get the data from all those platforms, you can generate different images and you can use it for various applications. And here it shows that how optical images will look like, and how lidar data will look like, and then how the synthetic aperture radars data will look like. We'll talk more about those data in the lab sessions. So when we talk about remote sensing, whether like people are confused, like be like, is it a science or a art? So it consists of various mathematical tools, like development of various kind of sensors which can capture the different energies, So in that term sense, we see then remote sensing can be considered as a science. But when we talk about the data which we have obtained through the remote sensing, so to analyze or interpret those images, we need experience, which will come with the time and your creative thinking. So in that sense, if we see the interpretation part of the remote sensing data, then it is considered as an art. So it's a combination of science and art, which combines the various fields such as GIS, remote sensing, cartography, surveying, and then once you combine everything together, like remote sensing is the collection of data without being in contact with the object, then whatever the data you will get through remote sensing, you will consider like combine, like visualize the data and analyze and process the data in GIS softwares. You will use survey and cartography principles for the validation purpose and initial checks. And then once you combine everything, you can use it for various applications such as for biological science, social science, and physical science as well. And then next, if we see like what kind of analysis or with what kind of problems we can solve using this remote sensing data. So there it can be like classified into three different categories. So the first problem which we can solve using remote sensing data is a classification. So here classification, it means like what do I mean here? Classification is someone has given you an image and you have to classify that how many water bodies are there, how many forest area is there, how much irrigation area is there, or how much farms are there, how many urban like buildings are there. So you have to classify the given image into different segments or different class. That is known as a classification. If you have an image of any farm field, so you can classify that particular image into different crops, whether it's a wheat or rice or jowar or any kind of cotton or anything it can be. So you have to classify the different image. You just take one image and classify into some meaningful classes, which can help you to understand the phenomena. Then after change detection. So earlier in classification, we are just using one image. But now for change detection application, what will we do is that we will consider one image from 2000 and one image from 2020, and we will see like what is the change which happened in the last 20 years. If we are taking any cities, so how that particular city has expanded over this 20 year, it which are the location which are susceptible through the urban haphazard urban development, and how the lake surface area is changing over the time, how reservoirs are changing, how forests are changing, how deforestation is happening. So those kind of questions we can answer using change detection analysis, where we are considering two different image of same location. Then the third one will come as a time series analysis. Now, when we talk about, let's say, reservoir or any reservoir, so one water body is there and you want to monitor how the water level is changing in that particular water body. So what we have to do is we have to collect the image of that particular water body every day. So if we consider like every day or every week, we have to collect the image. And then after, when we compile each and every image, and then what we can do is we can make a GIF out of it, which will show us that how the water area is changing over that particular lake or over that particular reservoir, which will help us to understand the spatial dynamics of the reservoir. Similarly, if we have forest area, so how the forests are becoming dry, which are the parts or pockets which are sensitive to the change in rainfall, where we have to focus more. So those kind of things you can analyze once you have all this data of time series. So one data in of January, February, March. So you can make a like one bundle of images of the same area, which will help you to understand the like what is happening at that particular location. So he's as you can see here that it's a comparison of two different location or the time series analysis or single location. So which is very useful for classification. So this kind of, when we do the different kinds of problems, it falls under this three main criteria, and then there will be sub criteria under this particular three main three criteria. Now, when we talk about remote sensing, so there are advantages. So, in the advantages, major advantages, we can collect images of any particular area without harming the environment. So it is like passively recording the whatever the radiation is which is reflected going back or the emitting from the object of interest. So because of that, we are not disturbing the object which is there. Let's say forest, or if you want to collect some data from the forest, you will go inside the forest and you will take the data. While going inside, you will disturb that particular area which is sensitive in nature. And sometimes it is possible that we cannot go inside the forest, or some locations are there which is not accessible. So we can access those kind of area using the remote sensing data sets. Apart from that, like we can collect the very continuous data set and we can remove the sampling bias. So here, when we do the ground survey work, then if let's say at some location we went to do survey, we are measuring the elevation of particular site, that how elevation is changing at that particular area. And let's assume there is a big hill which is very steep in nature, and you do not have any instrument so that or so that you can climb on that particular hill and take the readings from that particular hill. So in that case, what we will do, we'll take the normal, if this is at this particular level, this might be 2 or 3 meter up. So that kind of thing we will write in our observations. So it will introduce a bias in the data which we are generating. So when we talk about remote sensing, it will exclude all those sampling bias, which is coming because of the human error, or the site is not accessible, or any other particular reason. Then we have like a control, like conditions. So uh, what is happening, like we can collect the X, Y, and Z data, where the Z data will be anything which is like elevation, depth, biomass, temperature, moisture content, rainfall, temperature, soil moisture. So it can be anything which is varying spatial in nature. We can measure that using this remote sensing data sets. And then when we talk about the limitations of it, so every time sun will not be there. The first answer is, like, if we take the simple monsoon season, there will be clouds and we cannot penetrate through the clouds if we are taking just energy from the sun, because sun is not visible during this monsoon season because of cloud. So we need some techniques that normal active sensor will not be possible. So where we are taking the help from sun, that that kind of remote sensing, which is known as active remote sensing, that is not possible during the monsoon season and when there is obstruction between the like source of the energy and the object in which we are interested. So for that we need different kinds of electromagnetic waves or some other instruments such as lidar, radar, sonar, which can go to the particular object, and while doing so it is intrusive and it will affect the nearby area, so which we are investigating. So that's why like we need active sensor, and active, when we are going to use active sensor, it will affect the nearby locations in somewhat way. Then we have remote sensing instrument. It we are taking the data from satellite. So if there is like a problem in the calibration or in some the constant of the satellite, then it will create a malfunctioning of the data sets or error or bias in the data. And then after, the next limitation is like remote sensing data may be expensive to collect and analyze because we are using drones, aircraft, or some satellites. So it will be like very costly in nature. So there will be a good trade-off between like what area, between the like area which you are going to investigate and the money which you are going to invest in the project. So if you have like what kind of accuracy you need, and then what kind of information you want to collect, so based on that you can find out like whether to go for the remote sensing using which platform, whether it's airborne, lidar, or satellite based, or aircraft based, or anything else. So now what we will do, we'll take some of the questions on these concepts. So the first question is like, which model has the building height information? So this is the data, DM data, which we have you have learned in the first week, like the first lecture of this week, where is talk about the various data related to the height or elevation. So there is a three different terminology: DEM, DSM, and DTM. digital elevation model, digital surface model, and digital terrain model. So which of the model is giving the building height information out of these three?
So elevation model.
Option
Option A.
A. Anyone else? So here the right answer is D, ASM, because like when you talk about the data sets, then DEM is very general in nature. So DEM is like bare earth, and then like bare earth, which you can see here, the black line, which you can see here, which is like barren surface of the earth, that is known as a digital elevation model. So without considering tree, house, or any other object which are present on the earth. So that is known as a DEM. Now if we add some linear features, let's say ridge line or some other linear feature into our DEM, then it is a considered as a DTM, digital terrain model. So I mean DEM and DTM are both are more or less similar, but the thing is DEM has some more information compared to the DTM. So both are representing barren earth. And then when we talk about digital surface model, so here it means S word is only specifying the surface. It means whatever the satellite is taking, whatever it is seeing, it is directly taking the height of it. So if you are, it will consider the canopy of house or canopy of the tree rather than considering the barren earth. So when it is asked for, you want to get the building height information. So it is capturable through DSM, digital surface model, not from the DTM or DEM, which are the bare earth models. Is it clear?
Yes, sir.
Okay. So what we will do is in this today's lab class, we will try to see this concept using the real life data as well. So we will just see this thing in the just few minutes. Then the next question is choose the correct statement. So the first option is a DTM may be interpolated to generate a DEM. So if we have DTM, we can create a DEM out of it. The second statement is DEM and DTM are same. Then the third one is TEEN is a raster data and DEM is a raster data. So can anyone wants to try?
According to the earlier statement, DEM, DTM are same you told in the previous
So
question.
yeah, so what I told is more or less they are same, but there is a difference, which is a minor difference that in one of it you have some linear features associated with that. So DTM is like bare earth, and then you have when you have linear features out of it, you can generate the DEM model. So if you have DTM, which is digital terrain model, you can generate the DEM out of it. But if you have DEM, you cannot generate the DTM. So it is like some of the extra features are present in the DEM, which is not in DTM. So almost they are same, but little bit difference is there. That's why we are going to remove the second statement. This is like very minor difference is there. And when we talk about raster data, so DEM is like continuous in nature. So that's why it is considered as a raster data set. So the fourth option is correct. Then this second option, DEM, DTM are same. So they are not exactly same. There is a minor difference, which is like if you have DTM, you can generate the DEM data, but if you have DEM, you cannot generate the DTM data sets. So using DTM, if we interpolate it, we can generate the DEM data sets. So option one is also correct. And then when we talk about this TEEN data, so TEEN is triangulated irregular network where you are fitting your surface with the so many triangles which are not exactly in the shape. So it is like overlapping your surface. So it is not considered as a raster data set. So the option here, the option the first and the fourth one are the correct one, A and D. Any doubt in this?
No, sir.
Okay. So now the next question is digital photography, photogrammetry. Basically, what we are taking through the satellites or the other platforms, airborne platforms, which we have seen earlier. That is also known as which kind of photogrammetry? Yeah, it's option number D, soft copy photography. Then the next question is the input data for digital photogrammetry is R. So if we want to create the DM, if you want to create DM or something like digital photogrammetry, if you want, so what kind of data will help you? So here DM is the data which you are collecting through your satellites or the sensors. LiDAR is also one type of sensors. So this first two are the data products, and then you can see here it's word digital photogrammetry. It means you are collecting photographs. The first two are the data, but the third and fourth are like what you can see afterward, like LiDAR and aerial photographs. So they are like photographs which will help you to generate the 3D models. As you have already seen in the past 2 weeks also, that if you have a photo of same location from different angles, you can generate a 3D model out of it. So if I just have camera, if you just install inside the Google 3D app or 3D Studio, what you can do is you can just consider one object and you take that object with a photo of that object from different locations, like keeping your phone like this, then like this, like this. So take a photo from different angle and then give it to this software. And then what the software will do, it will create a 3D object out of that particular photo. And like on Google Maps also you have seen such kind of 3D places or 3D locations. So we have like scanned aerial photographs and LiDAR. So these two can be useful to generate the digital photograph, like digital models using this photogrammetry principles. Then the next question is remote sensing techniques make the use of which waves?
Sir, I will electromagnetic
Uh, I didn't get your voices. So the correct answer here is electromagnetic waves. So it's electrical waves and magnetic waves, and it's like both are aligned at a 90-degree angle. So the correct answer is option C, electromagnetic waves, not electric waves and sound waves. It's electromagnetic waves both.
So I have a question from the question 4, sir.
Yes.
Why the ortho photos won't be correct here? Because the ortho photos are also that been corrected for
So
perspective.
yeah, in orthophoto, what we are doing, we are collecting the data at 90-degree, like exactly at 90-degree. So after that, we will not get any kind of relief or parallax. And because of that, we cannot construct the 3D model out of it. You have seen in the last week that when we have some angle or some relief or parallax in the image, then and then we can consider create a 3D object out of it, or we get the idea about the height information. So that's why the orthophoto is not a correct answer here. Is it
Okay, sir.
okay?
Yes, sir.
Yeah. So now we will go to next one. So just a minute, I will admit. So now the next question is, which is not an element of remote sensing system? So who wants to answer this?
Option C, refraction.
The option number C, refraction. As we can see, sun is a major source from which we are getting the energy. Then we have satellite images, which is like this step at the interpretation and analysis part. And interpretation is means the final interpretation and analysis, which will be making the data ready for the application. So reflection is a not a part; it is a process how the your electromagnetic waves are like interacting with the object. So now, when we talk about this electromagnetic waves, So what is a wavelength for visible light which humans can see?
Sir, 0.3 to 0.6.
Uh, no. So the if you see this thing, then your answer is zero point 0.4 to zero point 0.7 micrometer. So when you talk about zero point 0.4 to zero point 0.5 is like blue wavelength representing blue, zero point 0.5 to zero point 0.6 is green, and then zero point 0.6 to zero point 0.7 is representing red. So RGB like that, 0.7 to 0.6 R, 0.6 to 0.5 G, and 0.5 to 0.4 B. So that is a visible spectrum, and if you want, like you can make it in the 7 different components, so you will get the colors of rainbow. So main idea is visible remote sensing, and this particular portion of electromagnetic sense portion, electromagnetic waves, we can visualize through our human eyes. That's why it is being useful as a major part while doing the remote sensing application, because more amount of light is reflecting through this particular window of the electromagnetic spectrum, and we can also make a use of it to interpret the various objects out of it. Then after, if we go beyond, and that's why it's known as optical remote sensing in this particular region, which you see from zero point 0.4 to around 3 micrometer. So that is known as optical remote sensing, where the reflection is taking place. So what is happening, like how you are able to see, let's say this particular flower is there. So why you can see that particular flower as a yellow color. So light is coming at to this particular flower, and this only yellow color which is reflecting back, and others are being absorbed. So this reflection, what is happening at after interacting with the object, which is responsible the colors which you are seeing. So that's why, like, it is using a principle of reflection, reflected energy. Then we go from 0.7. There is then the next region is known as a infrared region, which is from zero point 0.7 to 100 micrometer. Entire region is known as the infrared region. Now in infrared region, it is happening through two different mechanisms. The first mechanism is reflected energy. So it is same as the earlier one, which is happening in the visible. That light is coming, it is interacting with the object, and it is reflecting back to the satellite. But the difference between visible and this reflected infrared energy is that we cannot see this energy through our naked eyes. Animals can visualize this infrared region, but we can't. So that's why we need some sensors which can capture this infrared energy from the remote, like up from the objects. So it is using the same principle of reflection, which is from 0.7 to 3 micrometer. Then when we go from 3 to 100 micrometer, you can see the name is thermal infrared. So why the name thermal here is because when we talk about this particular region, we are not using the concept of reflected energy. We are using the concept of emitted energy, because every object, according to the black body radiations, it is absorbing the energy from the sun, and then after it is releasing that energy through the atmosphere. So that is a outgoing radiation from the object. It is ranging in this 3 to 100 micrometer region, which is not the thermal radiation according to the black body radiation rules. So that's why, like, it is known as the thermal infrared radiations, and where we are using the concept of emittance, basically the emitted energy which is being emitted from the object to measure the that particular to answer, like to detect that object. Let's say two different rocks are like uh, like if you have two different balls, one ball is hot and one ball is very cold, iron balls. So how will you detect that which one is like hot and which one is cold? So what will happen, like the hotter ball will emit energy which is more compared to the colder ball, and because of that you will get more thermal radiations which are coming from that particular ball. And like that you can identify, like thermal guns also you have used during the COVID time. So basically here the concept which we are using is emittance, the energy which is being emitted from the object according to black body radiations. And the principle of remote sensing which we are using in the first two, visible and reflected infrared, is the reflection of the energy. Then we have microwave region, which is ranging from 1 mm to 1 meter. So here we are using the principle of scattering, that this wavelength are very quite big, quite big compared to the visible and infrared, from ranging from mm to meter, and so that it can penetrate to the different objects such as clouds or the tree canopy. So when we are not able to see what is happening at the ground using the visible or infrared wavelength during the monsoon time when so many clouds are there, what we can do is we can use the microwave region to collect the data about the Earth atmosphere or Earth surface, which is ranging from 1 mm to 1 meter, and it can penetrate through the cloud also. Similarly, if dense forests are there, so if you want to see what is inside the forest, we can fit the microwave sensor or the sensor which are ranging in this range to our drones or aircraft, and we can get the information about the below ground as well. So here we are using the concept of scattering basically. And then this radio wave region, it will not be useful for monitoring the something, but it will be useful for transmission of data such as your televisions or the radio signals which you are getting in your mobiles or the televisions, and so on and so forth. So it's useful for more for telecommunication purposes. Sorry for the disturbance. So basically, when we talk about this electromagnetic spectrum, it has like ranging from ultraviolet, which is also not that much recognizable in the different sensors. Like energy which is being reflected through the ultraviolet is very less. Then we have visible and infrared, which is using the concept of reflected energy. Then we have thermal infrared, 3 to 200 micrometer, which is the using the concept of energy emitting from the object. So emittance, which is according to the black body radiation rule, which is from 3 to 100 micrometer. Then microwave region, which is using the principle of scattering, and then radio region, which is useful for the telecommunication purposes. So now based on this, the next question is, which of the following wave is not employed in the remote sensing, which we are not using for remote sensing purpose? Yes, so the
Sir,
answer
I
is
think thermal infrared.
no. Thermal infrared we are using, as I said here, that thermal infrared is a part of remote sensing only. Okay, but we are not using X-ray because that is a very shorter wavelength and it is being scattered while reaching to the bare surfaces. So we are not using the X-ray. We are using this thermal infrared, visible rays, and radio waves. Is it clear?
Yes, sir.
Okay.
Yes, sir.
So now we'll go to the next one. So now when we talk about the remote sensing, so when the radiations are coming from the sun, it will interact with the atmosphere or interact with the object. So in that duration, what will happen is there any question? Okay. So what will happen while the radiations are coming from the someone's mic is on. Okay, so what will happen that when the radiations are coming through the atmosphere, it will interact with the molecules which are present in the atmosphere. Now consider that this is the wavelength which is coming through the sun, and these are the molecules which are present in the atmosphere, such as gas molecules, then smoke and dust molecules. So this will be gas molecules in the upper 4.5 kilometer. So there will be different regions of the atmosphere where these molecules are present. Smoke and dust will be like in the upper 4.5. This is for 6.5 or something, I guess. So you just check, verify that numbers with the slides exactly. And this, so depending on the size of this molecule, it will interact. and scattering will happen. So if the size of the molecule with which these radiations are interacting is smaller than the wavelength, then relay scattering will happen. If the size is equivalent to the radiations and the which is coming to the particular molecules, then it will scattering will happen. And when the size is very large of the size of the particle is very large, then non-selective scattering will happen. So based on this, now if you want to say which of the option following option is incorrect. So any idea? So one more thing, like when you see the, I will just give you some example through one concept. Then you have seen the sunset, okay? So during sunset or sunrise, you can see the different colors such as red and oranges colors in the sky. So why you are able to see those colors and not the other colors? Because when the radiations are coming from sun to us, it like scattering is happening, and because this shorter wavelength, like you have seen that thing that when you talk about this thing, so zero point 0.4 to zero point 0.7 if you go, then RGB, so it means R is having zero point 0.6 to zero point 0.7, then G is from zero point 0.6 to zero point 0.5, and then B is zero point 0.4 to zero point 0.5. So the shorter wavelength, let's say blue or green, are getting scattered very easily through the atmosphere, and because of that, whatever radiations which are remaining at the end is like red radiations. And that's why you during the sunrise and sunset time, you can see the sky as a orangish or reddish color. But if you see during the daytime when sun is on our top, we can see the sky as a white color or bluish color. So at that time what is happening is like radiations are coming, and first in that particular path, scattering is happening with the blue radiations, like blue waves which is coming, which is from zero point 0.4 to zero point 0.5 micrometer, and that's why we can see the colors as a bluish color. Then as the sun is going down, what will happen? The distance between us and sun will increase because it will go towards the horizon. So in that sense, what will happen? That blue lights which is coming to us, like it is getting scattered in the way, and like while it is coming to the us, whatever the blue light is there, everything is got scattered before reaching to us. So whatever now is remaining is a reddish light. So that's why you are seeing that the scattering of blue light is already being done, and then now is scattering being happened with the larger wavelength. So that's why you can see during sunrise and sun time when the sun is horizon, the distance between us and sun is high. At that time, you can see the colors like reddish color in nature. So now, based on this natural example, you have to tell like which of the wavelengths will scatter more, whether it's a shorter one or the longer one.
The shorter one will scatter more.
Yes, such as blue will scatter more and compared to the longer ones. So the option number B, which you can see here, the longer wavelength scatter more than the shorter one. So that option is incorrect. Then the next in this scattering. So the scattering is like we do not know the molecule size, we don't know the radiations which are coming and how it is interacting with the object. So it's not a very easy process to predict. So that's why the option number C is also incorrect. So this is option number B and C. Then relay scattering is happening in the 6.5 upper kilometer. That is also wrong, which is I think it's happening in the 4.5 kilometer of the atmosphere. So when you see this stuff, you in your lecture. So you will see these things in your lecture when like in the third week. So in the last lecture, where it is given that how it is interacting with the various objects. So if you go into that, you will see like why you are able to see different colors, like how scattering is taking place. Why you are saying this red and yellowish color during the sunrise and sunset time. Then after, what is happening with the different molecules, and then so this is the reflection which is happening, which is the principle which you are using for optical remote sensing for visible and optical infrared. Then this is the scattering principle which we are using in the microwave remote sensing. So color of the atmosphere due to, so here you can see the sun is away from us, so all the blue lights which is coming, it will be scattered, and the light which is reaching to us is red only. But as the sun is near to us or it's just on sky, it will give scattered blue light more. And you can see now the example relay and Mie scattering, which we have seen that if the molecule size is less, the relay scattering will happen, and if it is similar, then Mie scattering will happen, and if it is too much, then the Mie scattering will happen. And here you can see it is having a relationship of like 1 to lambda 4. It means the shorter the wavelength, higher the scattering, which is proportional to the 1 to lambda raised to 4. And you can see these regions which are being marked here, that the relay scattering is happening in the upper 4.5 kilometer of the atmosphere, and then the Mie scattering which is also takes place in the 4.5 kilometer. So you can see like which kind of molecules which are present during that particular, so gas molecules and smoke which are present during the 4.5 kilometer of the atmosphere. That's why that option is also incorrect. So any doubt in this question?
No, sir.
Okay, so now we will move to the next one. So which is the particle size found in the non-selective scattering? So when you are having this non-selective scattering which is happening, where the size of the molecules is very large compared to the radiation which is coming on. So what might be the size of the molecules? So generally water molecules are, so what might be the answer? So the first thing is like you have to think about like this particle size is very big. So in that sense, if you think like the option number A and C are incorrect, that it is a size lesser than 0.01 micrometer and 1 micrometer, which are very small in nature. So you have seen also the electromagnetic radiations as well. So this option like lesser than this is also already like you can neglect those two. Then answer like zero point 0.1 micrometer and 10 micrometer. Two are like the two will remain. So if you consider like 0.1 micrometer, so if you see that RGB color, which you have seen earlier in electromagnetic spectrum, that are also at the range of 0.4 to 0.7. So if the particle size is like greater than 0.1, it means that it is similar to visible like wavelength around zero point 0.4 or point, because the wavelength of visible spectrum is 0.4 to zero point 0.7, and if it is greater than 0.1, so it is also in the range of that. So it means that it will moreover like cause the Mie scattering rather than causing the non-selective. But the condition for non-selective is it should be very high compared to the radiation which is coming in. So the answer will be like 10 micrometer. So with greater than 10 micrometer. Any doubt in this one? So this is like remembering based, but you have to think logically so you can answer this thing very well. Any doubt? One more thing which I want to highlight over here. So you have to remember that particular equation which you are having, that scattering is directly proportional to the 1 raised to lambda to the power 4. It means the shorter the wavelength, higher the scattering. So now we will solve some of the questions which are from the GATE examination in geomatics engineering. So which is based on the similar concepts. So Now the next question is like electromagnetic spectrum can be broadly divided in which of the different segments, and you have to name those segments in order of their increasing wavelength. So what might be the right answer over here?
Option D.
Option D. Option D. So gamma rays, X-ray, ultraviolet, visible infrared, microwave, and radio wave. Anyone wants to answer? Anything else? So
Sir, I think it start from X-rays.
it's from gamma rays. Gamma is very small than X-ray. So what you can see is if you do not know like from where it is starting, you can focus on the last portion also. So we know that if you are confused between the option number A and option number D, what you can focus is which one will come first before like a wave first, radio wave or microwave. So in the electromagnetic spectrum, we have seen that 3 to 100 is like infrared, and then 1 centimeter to that in 100 meter around, it's like microwave, and then after radio wave. So infrared, microwave, and radio wave. So the only option which is like correct as per the last, comparing the last three, it's like D only. So that's why just go with the D. Now this relationship between this wavelength, frequency, and velocity. So what is the relationship between the C, V, and lambda? So can anyone tell the answer?
Uh, uh,
Yes. Which is the correct answer here?
So the
So when we talk about
Sir, option A.
part of
Option
the
A.
C.
option A is not right. Option C is right. So when we talk about the velocity of
Say
light,
option C. Option
yes,
C.
yes. So C is equal to F lambda. Generally, you told like just think about that. So V lambda or F lambda frequency we can represent using F or V. So like multiplication of this frequency and this wavelength is equal to the speed of light in space, which is 3 into 10 raised to 8 meter per second. So option number C. So this is like based on this, some numericals will be there where you will be given like a different frequency, that if you have 30 megahertz frequency or 30 gigahertz frequency or 30 hertz frequency, what will be the corresponding wavelength? So value of C you have to consider 3 into 10 raised to 8 meter per second, and then they will be given like any particular wavelength. Let's say if we want to say visible spectrum, so which is like what is the frequency of visible spectrum. Let's say the question which I asked. What is the frequency range of visible spectrum? So how will you approach the problem? So my question is, what will be the frequency V of visible spectrum? Now visible spectrum is ranging from zero point 0.4 to 0.7 micrometer. So visible spectrum is ranging from 0.4 to 0.7 micrometer. So what will be the corresponding frequency? So this is the wavelength of visible spectrum, which we just learned now. Now what you have to find is, you have to find out the frequency
So the,
associated with it.
so the lower limit will be 7.5 into 10 to the power 14.
Yes. So how will you approach? Like you will put this formula, C is equal to V into lambda. Okay. Then after you will put the value of lambda over here one by one. The value of C will be 3 into 10 to the power 8. So 3 into 10 to the power 8 meter per second. So you have to convert the unit properly. Then after, the wavelength is in micrometer. So you have to convert it into meter. So we will be same here, and then here you have to write 1.4 and then 1.7. So 0.4 micro is like you will multiply with the 10 raised to the power 6 minus 6. So it will be like converting from micrometer to meter. So you will find the frequency like this. So corresponding with 0.4 and 0.7, and you will get the frequency range. And similarly, they can ask you if the microwave radiation is 10 megahertz or 10 hertz, what will be the corresponding wavelength of that particular region. So that kind of questions will be there. Now we go to the next one. So in active remote sensing, so earlier I talked like what is a source of energy in remote sensing? So what is the source of energy when we do the remote sensing? From which source the energies are coming to the earth?
So sun.
Yes. So from sun the energy is coming. So that is our main source. Okay. So if you are getting energy from sun, then it is known as a passive remote sensing. And if you are having your own energy source, let's say torch or any other source, like just torch is an example, but you have your own energy source which is emitting the radiations, then it is known as a active remote sensing. The idea is active remote sensing, it means you have your own energy source instead of sun. So just keep that word in mind. Now in active remote sensing, it means you have your own energy source of earth object from the satellite borne sensor. The source of energy used for sensing lies at, अब आपके पास सन नहीं है तो आपको सोर्स कहाँ रखना पड़ेगा इंस्टेड ऑफ सन? Satellite. Okay, so you have to mount your source on satellite, which will act as a sun and it will emit the energy. So the answer will be satellite or any platform from which you are measuring the data. Whether it might be a drone, it might be aircraft or aeroplane or helicopter. So any airborne platform. So now the next question is, now which of the following statement or is or are correct? So how many of the statements are right over here? So what we learned while discussing the electromagnetic spectrum is there is a three way through which energies can be recorded in the remote sensing. The first one is the reflection, the second one is the scattering, and third one is the emittance. So first of all, I will just give you the brief so that it will help you in the question. So sun is there, let's say from sun energy is coming, so that energy is interacting with the surface and that energy is going back. So this is known as a reflection. Okay, just simple reflection. Now the second thing is energy is coming here to the surface, but what will happen is that the surface on which the energy is falling is like rough in nature, so it will not reflect like this, but what will happen that it will disperse in the different directions and diffusion of energy which is coming to the surface will happen. So that is known as a scattering. And when this diffusion will happen, what will happen that satellite will capture this diffused energy. Okay, so this energy satellite is capturing. So moreover this diffused energy, more you will get the information about the object. Okay, so because if the energy is just not surface, like in real life, like we will not see any surface which is very smooth. So most of the time this diffusion will happen, and then your rays will be like diffused in the different directions, which you will measure through satellite. Let's say your satellite is mounted over here. So this is your satellite. So satellite is capturing the energy which you are getting. Okay. So now you have to, based on this, and the next one is the emittance. So emittance is means this object, like now the energy which is coming to the surface, some of it will be reflect, some of that energy will diffuse, and some this land will absorb. And whatever the energy it will absorb, it will emit during the night time, and that satellite will capture. That is considered under thermal remote sensing. So now based on this thing, just try to give this answer. I'll give you 1 or 2 minutes. Just think about it. We will discuss each and every option afterward. So now we'll start with the first option. Okay. So in optical remote sensing, more often we are interested in diffuse reflection. So that statement is right or wrong, first of all. So is it right or wrong? The first option. Anyone? So what do you think? I mean, in remote sensing, what is necessary? If you take optical remote sensing, thermal remote sensing, what is the core principle? Is reflection. Okay, so yes, in need we are interested in diffused reflection, which is coming back to the satellite. So that's why the option A is correct. Then we'll go to the second one. The reflection will be diffused if the incident wavelength is comparatively much larger than the surface roughness. So the wavelength which is coming over to the surface, if it is too much, then the diffusion which is happening is more. So is it right or wrong? So think about the case when we learned about the scattering mechanism. Okay. Now in scattering mechanism, what you have to think is, so what you have to see is like you have these gas molecules. Okay. Now this wavelength which is coming to the object is very big compared to this molecule. So what will happen? Whether it will diffuse or it will just pass away. So what do you think? Whether the diffusion will occur or not, if the wavelength which is interacting with surface is too much big.
So diffusion will occur.
So it's wrong because diffusion will not occur. Why? Because your object is very small. The reflection will be diffused. So your object is very less, but your wavelength which you are having is very large. Comparatively much larger wavelength than the surface roughness. The surface roughness is this much, which you are seeing at the back, ground roughness. So if your wavelength is very high like this, what will happen? It will just pass away and it will not diffuse. Are you getting my point? So this option is incorrect. The first one is correct, the second one is incorrect. Why? Because if the roughness of the surface is very small in nature, then it will try to reflect back. Okay, why? Because like, see, consider something like which is very smooth. Let's say a smooth, calm surface of water. Or let's say I have just example like you have this kind of box with you. So if you have this kind of box, if it is very smooth, then what will happen that whatever the thing will come, it will just go away. But when you are like rubbing your finger like this, if this like surface is very friction, having very like too much friction, it means what? The surface is having more roughness. So you can feel that thing. If it is very smooth, you cannot, it will just go out. So what will happen like, well, if the surface is smooth, smooth means what? the roughness is very less. So here the same thing, it is being reflected. If the wavelength, it means your finger, if it is too larger compared to the surface roughness, then you will not feel that friction, and it will just, you will just pass through your hand, like it will just move like this. So if the surface is very, surface roughness is less compared to the wavelength, or wavelength is very high compared to the surface roughness, in other terms, diffusion will not happen, or it will happen very less. Then the third option is a surface that reflects microwave in specular manner may reflect the visible in diffuse manner. Now, what you have to focus here is, first word is microwave, and then another word which is given here is visible. Okay, so which one is having higher wavelength, microwave or visible?
Sir, microwave.
Microwave.
Okay, so the wavelength of microwave region is high compared to the visible. Okay, so to decode this answer, first we have to think in this way. Okay, now in the earlier question, what is the concept which we learned? If the surface roughness is less compared to the wavelength, it will not diffuse. It means just, it will just directly reflect back. So what it is showing here is a surface that reflects. Reflect means what? Surface is very smooth. Reflects in microwave in specular manner. Specular मतलब जो आ रहा है उसका सीधा रिफ्लेक्शन हो जा रहा है, डिफ्यूजन हो ही नहीं रहा. Okay, it means what we have to interpret over here, that microwave is having very large wavelength, and compared to that, surface roughness is very less. So that's why this reflection is happening, which is nature, specular in nature, which will just go like this, reflecting and going back. Is it clear? Now, in specular manner may reflect the visible in diffusion manner. Now what we are doing is, when we are going in the visible region, what is happening, that wavelength is decreasing. Now when the wavelength will decrease, what will happen? The roughness and the wavelength will try to match with each other, and when it will try to match with each other, the diffusion will happen. Okay, so earlier what was the scenario? That your surface roughness is this much big, and the wavelength which you are putting, the microwave wavelength, is also very large. But now what you are doing is, you are reducing your wavelength like this, because you are going towards the visible region. So what will happen if you have same the molecules or same the surface roughness? Now it will interact, and then it will diffuse a lot. So this option seems right, because if our wavelength is high, then it will reflect. But as we will reduce our wavelength, what will happen? That diffusion will start to occur. Like it will start to taking place. So that's why this option number C is correct. Then the last option is, all the wavelengths emitted by sun reflect in diffuse manner from the object on the surface of earth. So sun से जितनी भी rays आ रही है, सबका diffusion होता है. Is it right or wrong? Because from sun we are getting everything. So is it right or wrong?
Wrong.
Exactly. Why? Because yes, it is wrong, because from sun we will get the bigger wavelength, larger wavelength also, smaller wavelength also. So whatever is larger wavelength compared to the surface roughness, it will reflect, otherwise diffuse. So that option is wrong. So not all the way will diffuse. Some of it will reflect, some of it will diffuse. So like this, the correct options are option A and C. So like this is the specular reflection which is taking place, where the surface is very smooth in nature. But if you have some roughness because of topography or something else, vegetation or some other parameter, this diffusion will start taking place. And higher the wavelength, if the wavelength is high compared to the roughness of the surface, then what will happen, that it will just try to just ignore it, and then it will just reflect rather than diffuse it. So are you clear with this answer, or any doubt? Any doubt in
Clear.
this? Clear? Okay. Is there any other concepts which is not clear to you till now in this question? So this is like very simple question based on the fundamental which you learn, but you have to think a lot in this direction, considering the scattering mechanism, how the like object and the wavelength will interact with each other. Okay, so we'll now go to the next one. So the part of solar radiation incident on the water surface gets refracted. So refraction is happening as per which law? So which is the law which defines the refraction?
It's
Snell's
a
law.
Snell's law.
Snell's law.
Snell.
Okay. Yes. So option number B, Snell's law. Then the next question is, which of the following parts of the electromagnetic spectrum is or are used with the satellite remote sensing? So which part we are using in satellite remote sensing?
It's a thermal infrared wavelengths.
Yes, thermal infrared wave. This is a multiple choice question, so more than one will be correct.
The A, B, C.
A, B, and C. Gamma we are not using. We are using A, B, and C. Visible, which is point 0.4 to zero point 0.7 micrometer. Thermal infrared, which is from 3 to 100 micrometer, and the radio waves, which is a very, very high wave. So these are the questions based on the like GATE exam. So now, is there any doubt in this week's content? Anything which you want more clarification, or is there any part in which on which we can focus more? If not, then we will try to understand some data sets. So is there anything?
So the active and passive case in the remote sensing.
So we'll go to that. So when we talk about active remote sensing and passive remote sensing, so here you can see sun is there. So sun is radiating the energy which is passing through the atmosphere. It is interacting with the object and it is going back to the satellite. So satellite is measuring the energy which is being reflected from the object, and that energy is coming from the sun. So here we do not have our own energy source. We are using the energy from sun. So that's why it is known as a passive, that we are like depending on someone for the source of energy. So it's the passive mode. When in the other case, in active remote sensing, what will happen that the satellite will only have a source of energy. So it will first send the energy, it will interact with the object, and it will come back to the satellite one more time. So just from here only we will release the energy, it will interact with the object, and it will come back to the satellite. So that is known as active remote sensing, where we have energy source mounted on the satellite or the airborne platform. Is it clear?
Yes, sir.
Anything else? Any other question also?
So what is optical remote sensing?
Okay, so optical remote sensing, it means it is using a principle of reflection energy, reflected energy. So here you can see there is a three different phenomena through which remote sensing can take place. One is the reflection of energy, the second one is the scattering of energy, and third one is the emittance of energy, so emitted energy. So if we are using the reflected energy, it is known as a optical remote sensing. And optical, it means that like we can see like reflections. Like in the first optical part is 0.4 to zero point 0.7, and then is the thermal like infrared region, which is 0.3 to around 3 micrometer or something. So, yes, we are using optical rays, which is the main principle which we are using is reflection.
Okay, sir.
Anything else? Any other doubt from the content also you can ask if you have. Otherwise, from the content which we covered till now. So, okay. If not, then what we will do is first we will try to understand this DEM, DSM, and DTM through the practical data sets. So, for that, what we will do is first we will open one site. So, do you guys want to do the same thing along with me?
Yes, sir.
Okay, so what you can do is you can go to this site called as Open Topography. So if you have a laptop, you can try to do along with me. Otherwise, what you can do is you can just go through the recordings and you can do the same thing afterward. And from the next lecture, what we will do is I think you should download the QGIS in your system so that you can replicate the analysis also along with me, or some analysis on remote sensing data or some GIS data sets. So if you are more interested in the application part of the data sets, I can teach you the QGIS part. So for that, you can install the QGIS into your system. So like at the end of this lecture, I will give you some like links to download the and install the QGIS in the system. It's very easy. You just download the source and then just click on the next button and then it's done. So right now we'll talk about this elevation data sets, DTM, DSM and all. So you just open this site, Open Topography. So this site is like high resolution topography data and tools. So this website is giving the different kinds of topographic data which is collected over the world from different sources. So now what you can do is after opening this site, you can go to the data tab. In data, go to data catalog. So it will show you the whatever the data which are present on this particular site. And if you go to this data and find data map, then it will show you from which part of the world that data is available. So if you go to data and find data map, it will show you the region from which the data is available to you. So now you can see that there is so many data sets from the USA. Then there is very less data, that's less or no data from India in this. Some data from this part, the like Southeast Asia also data are there. So the source of data also you can see who produced the data source. So this data is from Open Topography. This is from USGS. So these are the provider which is providing this data. This is from NOAA. Then this is the community database. It means someone has collected the data for their own research and then they have dumped their data or they put their data for the analysis part for other persons in this particular website. And then this is the global and regional DEM. So data which are available for entire world. So you can select any data also from this, like whatever you want. So you have heard about more about SRTM datasets. So this SRTM dataset is available like for entire world. So you can see it's covering the parts of India also. Now, if you see some of the dataset, let's say Arctic DEM. So this data is covering this Arctic portion only. It is the elevation over Arctic region. Then this COP datasets, which is available at 30 and 90 meter resolution. That is also available for entire world. Then we have this Europe DTM. DTM means Digital Terrain Model, which is bare earth model. So this data is available for Europe region only. Then we use just DDL3 data sets. So you can like click on each and every data and you can see that whether the data is available for entire world or whether for India or for which country or region it is available. So USGS 1 meter data set. So DM data at 1 meter resolution. So that is available for US region only. Again, you can see the very fine boundary as well. And then if you see the USGS 30 meter data sets, which is available for entire world, or not world, this is for these regions in the USA, US only. So like this, you can explore that the data is covering the Indian portion or not. So once after doing that, now what we will do is you can either select the data from data catalog or from map. So now we will go to data catalog and we will see. So here few tabs are there, that open topography, high resolution topography, USGS 3-dimensional DEP datasets, NOAA datasets, community contribute data grid, and global and regional D. So whatever the factors we have seen in the legend in the map, same thing is given here. Now you can see here that there are the different data sets. that is mapping landscape evolution in this Ozark, Arizona 2023. So this data is collected in 2023. And you can see this is the point cloud and raster data. So point cloud is any data sets which are collecting through the drones and other LiDAR data sets. So you will get the data in terms of point cloud feature. So now let's go to this LiDAR survey to evaluate spatial heterogeneity and channel evolution. So we'll just look into one of the data sets. So this data set is collected using the airborne LiDAR sensor, and this is like for the purpose of channel evolution. Now in the overview, you can see about the who collected this data and for which instrument they used to collect this data sets, at which date they did this collected this data set. So they have collected this data in the 8th of August and through September in 2022, and then this is like so this is like 8th and 9th of August, and then they published this data in the 28th of November 2023. So who is the principal investigator in creating this data set? So how much points they have collected, how much area they have covered, what is the point density? So in every 1 square meter they have collected around 28 points. So you can consider that how good resolution this data is having. If you take just a 1 by 1 meter of pixel, it is having 28 number of data points inside it. And then you can see the resolution of the data which they are giving at 1 meter resolution. So resolution, it means the size of the pixel. We will see that in GIS software just after some time. Then this is the coordinate system. So whenever you are talking about geospatial data, you have to think about the coordinate system. Let's say X and Y. When you have X and Y, which coordinate system you are using, or basically axis you are using. So for that, they are using this UTM zone 12 north, which is in units are in meters, not in degrees. And then this is the vertical. So for when you are talking about elevation data, you will be having coordinate system in 2 dimensions. One is in horizontal direction, in one coordinate system in vertical direction. So in vertical direction, the coordinate system is geoid 18 EPSG 5703, and in horizontal is EPSG 63441. So when you want to combine different data sets with each other, then this coordinate system of different data sets should be same. And then you can match it with each other. And then this units of this data sets is in meter. Survey report, so you can find out how they conducted this survey to collect the LiDAR data sets, and then how they generated the reports. And then if you go down, it will show you this data is available for this much region only. So now you can go to this up, download and access the product. So now you can click on raster data sets, and then if you go down, you have to select the region for which you want to download the data sets. So how many of you are doing along with me? So yeah, if you are doing, so are you able to follow me, or should I reduce my speed a bit?
No, sir, you continue, please.
Okay, fine. So now if we want to download this data sets, I will click on the raster which was there. So here I will click on the raster data sets, and then after you go down and select the region. So this data set is having very large volume. So what we will do is we will zoom to the any particular portion, and then we'll go to the over here. This button is there. Select a region. So region for which you want to download a data set. Then after, just make a square or rectangle, whatever you want. After selecting a region, it will show you that you have selected area approximately 1 kilometer square. Okay, and if you want to enter the coordinates of that region manually, so you can do that also. Now the second thing is data output format. So we will use the same like format only, GOT format. Now layers which are available along with this data. So we have learned about two different data sets, terrain model and surface model. So terrain is a bare earth model and DSM is surface model where it will consider the height of building, height of tree or any other object which are present on the earth. So we will click on both of it. So we can differentiate between these two. And you can see here that in title they have written digital elevation models. So digital elevation model is a general stuff and DTM and DSM are a part of it. So where you are talking about in general elevation, the first data which will come in mind is DEM. Now DEM is distributed in two different ways, DTM and DSM. If you have DTM or DSM, you can generate the DEM using it. And then you have include global 30-meter SRTM data. So this data is available globally. So do you want to compare this globally available data set with the data which is captured through the LiDAR or not? So if you want to compare the data with the available data set at 30 meter, you can click over here. So if you over here, you can see SRTM data is at 30 meter resolution and the data which we are downloading from this site is at 1 meter resolution. So how it will make a sense? Like if you see this thing, so what I'm talking about is resolution basically. So this data which is available directly or for entire world, that is at 30 meter resolution. So 30 meter resolution, when you talk about 1 pixel, it is having a like dimensions of 30 meter by 30 meter. So 1 pixel is representing the area of 30 meter by 30 meter on land, which is through the satellite. Now when I'm talking about the LiDAR sensors, this DTM and DSM data, which are at very high resolution, at 1 meter resolution. So what will happen that I will divide this into 1 by 1 meter. Then how many number of pixels will be formed here? Can anyone tell? If I divide it into
900.
900 exactly. So what I will do is I will create this kind of line which are having 1 by 1 meter. So 30 horizontal and 30 vertical lines like it will say. So this will be like converted into very finer resolution. So now whatever the pixel you will get from this LiDAR is 1 pixel is 1 by 1 meter. So now this length and width of this pixel will be 1 meter. So total 900 pixel you will have. So you can like think about the volume which it will have in the storing the data set. When you convert your data from 30 meter to 1 meter, you need 1 pixel to 900 pixel. And if my area is 1 kilometer square, then how many pixels can come under like 1 kilometer square if I consider 30 by 30 meter? So the area which we have selected right now, it's 1 kilometer square approximately. So if I consider the grid of 30 meter by 30 meter, how many pixels can come inside the selected area?
So almost 1100 and more.
Exactly, 1100 and more. When I talk about 1 meter by 1 meter, how many pixels will come in?
1 million.
1 million pixels. So you can just consider the amount of volume which is being increased. Okay, so that's why the size it will be vary. So now you have to select this DTM and DSM and this SRTM data also. We will collect it for the comparison purpose. Now these are the visualization type. So if you are having elevation data sets, what are the things you can play with it? You can create the hill shade, color relief, slope, aspect, roughness. So I will explain these features one by one in the QGIS only when we analyze the data sets. Right now I will not do anything here. So I will just select one option here, hill shade. Then after we'll go down and canopy height model. So in the earlier week you have learned that if you have height information, what you can we can generate, like if we have this DSM and DTM, also. What you can generate is height of the building, height of the tree. So DSM is representing data barren earth plus tree, barren earth plus building. So if we are, what we do if we just take DSM minus DTM, what will we get? The height of the tree, height of the building. Are you getting my point?
Yes, sir.
So like that, we will find out the canopy. What is the height of the tree or height of the building? So we can just take the DSM minus DTM. So if you want that layer also, you can click over here. Then contour lines. So contour lines are the line representing equal elevation. So what are the elevation like pixels where the elevation value is 5 meter or 10 meter. So if you want contour line, you can click on this and you can generate the contour lines as well. And if you want to pre-process this data for hydrological purpose, you can click over here. But this option will be available once you will log in into this particular site. Then after the last step to download this dataset, you have to give your description. So you can just write, yeah, just a BTech student or PhD students or whatever students you can write. And then your description you can write in detail like a master student or PhD student working in the discipline of art science at IIT Gandhinagar. So that kind of description you can write, and then at the end you have to provide your email ID, and then you can click on submit. So once you will click on submit, it will give you the result of your job. And once this dataset is ready to download, you can just click on that data and download it. So you will just click on submit, and once this data it will extract, you can see this right information. This now the extraction is done, querying is done. So it will take some time depending on your internet connection. So now once it is done, you can see this download this data product. So what you have to do is you just have to click on the layer and then it will download the data. So the first data is the DM result. So I will just click on that 2.6 MB. The another one is, so you can see the 1 meter data is 2.6 MB, whereas the data of SRTM is at just 1.5 KB only. So you can see the volume here. So the SRTM data, which is 1.5 kilobyte, and this visualization. So visualization is in this format. So hill shades. So how will it look like? Okay, so like this, you can download this data. It will download the data as a zip file. So you have to go to your download folder and then unzip that file. So just right click and then extract all and then extract your data sets. So it will create a folder, and in that folder you can see your data sets. So are you clear with this data downloading part,
Yes, sir.
everyone? So now you can download any of the data sets from this particular website related to the digital elevation model. Any data related to the elevation basically. So once you will download the data, now you should have any kind of software which you can use to visualize the data sets. So basically this type of raster and vector data, we use this GIS software, which is Geographical Information System, which you will learn at the end of this course as well. So this software will be useful to visualize, process, analyze, and take decisions from the data which are geospatial in nature, such as the data which we downloaded just now. So what you have to do here is you have to go to the folder where you have kept your data sets. So I have kept my data under, so we have just downloaded the data. So now I will go to, I will extract both the data sets which I have downloaded. And now I will delete the zip files now. I don't need them more. So now, first of all, we will open the raster dataset. So if you want to just import this data in any GIS software, what you can do is, first thing is, you can go to the GIS software. You can click on project. So here you can go to layer and data source manager. You can go and you can select a path where your data is saved. So this is the raster dataset. So we will just click over here, and then after we will go to the folder where I have saved my datasets. So I will click on the datasets and I will click on open and I will click on add. So just it will add the dataset into my window. And the second way through which you can import the data is you can just select your data, drag and drop your data into any kind of software. So that will also be helpful in importing the data. So the first step is importing the downloaded data into your software. So now you can see here, this is the three different data sets. The first data, I mean the third layer which you can see here, this output SRTM MGL. So you can see the size of pixel. So this SRTM is at 30 by 30 meters. So here, if we want to measure this pixels, you can see. So they are at 30 by 30 meter resolution. So here one measurement line is there. I can just click and say. So it is, you can see it's around approximately 29.912 meter. So each pixel is having 30 by 30 meter resolution. And when I talk about the data which I collected through the LiDAR, it is at 1 meter resolution. So you can see the difference between these two data sets, first of all, that how fine this data will look like and the how coarse that other data will look like. Is that clear? First of all, the comparison between spatial. Now, if I zoom in and if I see any one, measure any one pixel, then you can see the width is 1 meter. So first of all, we have measured the width, and this concept is known as a spatial resolution. What if you want to read very high details on the surface, you have to take a increase the decrease the size of the pixel. It's from 30 meter we went to 1 meter. So that is increasing the spatial resolution in such a way that you can see more amount of details. Okay. So now here you can see we have downloaded three different products. So the first one is output SRTM GL. So that is a SRTM data which is available for entire world. Then you have BE and HH data sets. So now can anyone tell me which of the following is DSM and which one is DTM just through your inspection? So this is the value which you are seeing 956 and 978. It is the elevation value. Can anyone tell me which one is up from this two? Which one is
DSM.
DSM? Which one? Which one is DSM?
So the later one, the last.
No, just see the first two data set, output underscore HH and output underscore BE, which might be the DSM. And the value which we are seeing, it is the elevation value.
The first one.
First one, exactly. Why first one? Because consider the concept. What we talked when we talked about DSM and DTM, the DSM data is a surface data. It will consider the height of building, height of tree as well. And then DTM data is just barren earth. We are not considering anything. So data which is having higher elevation, it means that it is representing DSM, surface value. So you can see here this HH, that data is ranging from 957.14 to 1005.80. So that means it is a DSM data, and the another one is a DTM data, or you can see BE, which means barren earth. Is that clear?
Yes, sir.
Okay. So now that is just visual inspection. Okay. Now we will see, we'll first put imagery to just make sure that what are the parts that we are visualizing. to just check that thing. So now you can, I will just turn off the other layers. So now you can see this data is from this particular area. Okay, where you can see this images. So which are the features which you can see here? So which are the earth features which you can see here?
So the forest cover, the elevation,
Forest, then
of the land.
elevation of the land. So I'm talking about the feature. I mean, feature it means house or forest. Forest it means tree. So what else you can see here?
So some water bodies are also visible.
Exactly. So water body, plain land, some trees, and some bushes also. I mean, we can see some trees are like having very high height is more compared to some tree. And this some dark portion you can see. If you are seeing this particular tree, so if you see this tree, you can see some darker colors over here. So what might be that might be?
So darker colors are the bigger trees, and the lighter colors can be grasses and bushes.
Right, but see here you can see very dark color also. So that is not because of bigger trees. That is because of the shadow of the tree. Okay. So when we
Yes,
are taking the imagery during daytime, depending on the sun location, it will generate the shadow. And that shadow we are seeing as a black color over here. Okay. Now what we will do is now we will know the particular area. Okay. So there is one plugin in this which can like draw the elevation profile. So what we will do, we will just take one area and we will find the elevation profile. So first of all, I will put my DM. So I will put this too. Okay. So the HH, it means the DSM data sets. I will show it as a red color and then barren. Okay. So this data, which you can see, I will show with the red color and the barren earth data I will show with the black color. So, I mean, this tools plugin is Terrain Profile. If you do not have this plugin in QGIS, what you can do is you can go to plugin, manage and install plugin, and then you can go to this here, and then you can just write terrain, and it will show you this profile tool, which you can install, which will help you to make the profiles of different areas. Now, what we will do is I will just we will take one profile which is starting from here to let's say here. Now can you see here two different profiles? Can you see here two different profiles?
yes, sir.
So can you say which one is like DSM and which one is DTM?
So the higher spikes may be the DSM.
Exactly. Why? Because you can see now you can see how like if as I will move with the graph, it will also show me in the line also. Okay, so see here first plane is there and there is a vegetation but very which is very small bushes or some other vegetation grass. So that's why the difference between DSM and DTM is not that much. But as I am going towards this area, which you can see here, so it is covered by trees. So you can see sudden spike in the elevation in DSM, not in DTM, because DTM is the ground. Now, as I am going forward in this region, there is no tree. So you can see here, if I will zoom, there is one single tree which is giving this spike, and then after there is no tree, and then after there is a bunch of trees which are present there. So canopy also you can see the trees which are in the starting at are at where higher like their height is high, and as you are going from this left to right side, the height of the tree is decreasing. And then after you can see this is barren area, And then as you go forward, some trees canopies are there, and then furthermore plain area. And you can see in this plain area both the surfaces are overlapping with each other. It means there is no vegetation as well. It's like plain ground, barren ground. So are you clear with this concept now?
Yes, sir.
So now we will take one more example where we will see this river. So you can see wherever this, here the trees is there in the starting, that's why it is giving spike. And then as I'm going towards here, furthermore trees are there, so it will like canopy is increasing. And then around river there is nothing, so it is exactly coinciding with each other. So similarly I can do it with different river cross section also. So you can see now how the river elevation is also changing. So on the both
So
river
here
banks,
the
yes,
so the entire river beds is now clear from here. So the possibility of flood during monsoon season, that also can be tracked from there.
exactly, exactly. So these are the applications which you can follow furthermore. But the thing which now, if you are doing flood application, okay, which data you will consider, DSM or DTA?
DTM.
DTM, okay. So that thing you have to consider in mind that when you are talking about flood, you are not talking about building, okay. And then you can route your flow in such a way, so that it will just follow on land, not from the surface. So is this clear? I mean DTM, DSM, and this DM data as a whole.
Yes, sir.
Any doubt? Anyone? Okay, so if there is no doubt now, you if you want to download this data and you want to make a PPT or something out of it also, if you want to make river cross section also, you can go to table and you can just copy this data to your clipboard and then you can paste it into your Excel or something, and then you can also export it as well as you can just make a Python library which is using. So, so like you can use different plotting you can do, and then you can put this data into, save this as a PDF, Excel file or PNG file, whatever way you want to save it. And one last thing I will show you, this is the how this data will look like in the 3D. So I will do is I will just open this data. So all the data I will try to open. So first we will see with the SRTM data set. So if you want to add this thing, you can go to view, new 3D map view, and then over here instead of flat terrain, you can just write DM raster layer, and then you can select any layer. Exaggeration will take 5. So this 3D graphics will take some time because the data volume is very hard. Instead of flat terrain, you have to go to DM raster layer and then just select barren earth or. So I think with this volume, it will take bit time in processing those data because it is just 1 meter resolution. So what we will do, like today we do not have that much time. So I will try to show that in the next class. Meanwhile, what we can discuss is now when we talk about the Indian data set, what data sets to use. So now in India, when you went to this find data map, you have seen that there is no data available for Indian regions. Okay, so what you have to do is you have to use some data sets which are continuous in for entire world. So go to data catalog and then you can just click on global and regional. Now here in regional, global and regional, so you can see if you go down, there is a one data set named as SRTM datasets, which is available at 30-meter and 90-meter resolution for entire world. So you can see shutter radar topography mission SRTM global. So this is like SRTM 133 means it's at 90-meter and one is at 30-meter. And this is like a reference system which they have used is ellipsoid and here they have used geoid. So this is 90-meter and this two is at 30-meter for entire world. And this is the another dataset which is ALOS World 3D, which is also open data available for entire world. I mean, if you want to see that whether it is available for entire world or not, you just click on that particular dataset. Now go down and you can see the area which it is covering. So you can see it is covering the India as well. So you can see also that data is also available at 30-meter. But the thing which is interesting over here is you can read about the data description. So here when you read about the data description, it is showing this ALOS global digital surface model. It is not terrain model, it is surface model. It means it is giving you the DSM datasets rather than giving the DTM datasets. So it is giving the data of trees, buildings, and so on and so forth. So if you want to get the flood routing and so other applications, you cannot use these datasets. Okay, so that thing you have to consider while working with the datasets. So then after this ALOS Pulsar 3D datasets, then we are having SRTM datasets, which is also this shuttle radar topography mission. So if you go to this SRTM GL1, that is also available for 30-meter and for entire world. So you can see 30-meter resolution and for entire world. So you can download that data also for Indian regions. And this is the DTM datasets, which is collected around the 2000 or 2002. You can see here. So this collection date is around 2000. So you can read more about these datasets, how they collected the data. Then if you go down, there is one more data product, which is this Copernicus digital elevation models. So by just looking at the word, you will think this is just global elevation model. But when you just go down and read the description about the data sets, you will learn about that this Copernicus DEM is a DSM. It's not DTM. And you can see this terminologies, how they are using. So whenever they are talking about elevation data, this DEM word is very common. So we can see also like the DEM is a main idea about the elevation data and DSM and DTM are a branch of the DEM datasets. So here also you can see this dataset is DSM data, digital surface model, which represents the surface of the earth, including building, infrastructure and vegetation. This DSM is derived from an edited DSM version, World DEM, where a flattening of water bodies and consistent flow of river has been included. So here the another word which came is flattening of water body. Flattening of water body. So wherever the depressions are there, such as reservoir or lakes, they have flattened it out. So you cannot see the depth of reservoir or depth of the building, depth of the water. Because they have just flattened out the water bodies which were present. And why this thing is necessary? Because when you do the hydrological modeling, if that kind of depressions are there, your water cannot flow through the physical models, which is capturing the flow of water. It is just like there is a sink and whatever the water is coming from the top, it is just going in that sink only. So just to avoid that effect, they are flattening this water body for hydrological simulations. So this is like it. In addition, it is editing of shoreline, coastline, special features such as airport and impossible terrain structures has also been applied. So you can read more about this dataset. This dataset is also available for entire world. You can download this data. So there we talked about three datasets. One is the ESTER data, one is the SRTF data, one is the Copernicus data. Then you have some more datasets which are available. This NASA DEM global digital elevation data. So this is the also data is one of the byproduct which is of the set SRTM data. So they have collected the raw images of the set SRTM data sets, and then they have created this another data set which is NASA DEM data set, which is also available for entire world, as you can see here. And then this thing like the collection date is same only, but the publication date is in 2021. So they have done so many processing with the new tools which are being there in the market, and then it is giving the final data set after doing so many corrections. So this is also like which kind of data you can read about DSM or DTM in detail. So they have also merged this LOS pulsar datasets along with this. So you can read more about it, and you can see other products also which are available. So like that, you can download the various digital elevation models, which will give you the information about the elevation. That information you can put into the GIS software, and you can visualize and process those data sets. And you can also do different kinds of analysis onto that particular data sets. So this analysis part we will learn in this upcoming lectures when we talk about more about this remote sensing data in this other different GIS data sets. So before that, like if you are interested in downloading the QGIS, so what I will do is I will share a link of QGIS. So there are so many versions of QGIS which are available. You can download and install their latest version also from your just website, but I suggest you to use the version which is 3.16.9. So if you are Windows user, then I will just dump that link into your chat box. So what you can do, just click on this link and download the data. So download the QGIS, and then just go to your downloads, double click on that. It will open. Do you want to make any change? Click on yes, 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 next, 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 and it will install this QGIS into your system. So if people are interested over here, I can teach you QGIS in the next lecture after completing our normal syllabus or normal question answering session. So you can just install this version of QGIS. So it is like compatible if you are doing hydrological analysis. And if you want to download the latest version, you can go to this QGIS main site, QGIS download, and you can just click on download QGIS from the website. So you just go down, skip it, and go to the downloads. This is the like open source software. So if you want to donate, you can donate anything. Otherwise, just skip it and just go to the downloads. You can click on long-term version for Windows. So you can download the version for Windows also. If you for Linux, Mac or other versions, if you want to download, in this also if you want to get some older versions like 3.16 or something, you can go to archives, and you can like see the different other archives or like older versions also you can download from this. And the better is to, if you are interested in hydrological analysis and so on and so forth, you can download the main version which I have told you to install, 3.16.9. It is quite compatible with the hydrological analysis and other analysis. Some of the current versions are not compatible like with hydrological analysis, because in that they are using some higher versions of Python, and the libraries which are necessary to run for hydrological analysis, they require some older Python version. So there is a clash between this Python version. Yeah, because of that, I mean, I prefer use this 3.16.9 version. So That said, I mean, for today's lecture, I mean, do you have any doubt or any suggestions, any way we can improve this learning in a more good way? Anything?
No, sir, it's great already.
Okay, so the next thing, if you want to use QGIS, just download it and install it. We will start using it in the next. If you have any problem in installing and downloading QGIS, please contact me on my mail or write in question answer session. I will try to reply in 2-3 days within the your question. So yeah, apart from that, if you want to learn, if you're confused between anything, you can just ping me on the question answers forum. Anything else? Okay, if not, then thank you for joining, everyone. We'll see you in the next Monday. So this next Monday is Raksha Bandhan, but just try to come on that day as well. We'll try to cover some interesting stuff and some interesting question we'll try to solve. So thank you for joining. Good night. See you everyone.
Good night, sir.